Hello everyone, we are Group Bcrypt and today we'll be presenting our Phase 4 demonstration for the Digital Signature project. Before we begin, let me introduce my team members. In this phase of the project, we were given several tasks. First, we were required to use different algorithms for the hash function, the public key and the signature scheme compared to what we used previously. Next, we need to measure both the time and the memory performance of our implementation using 3 different message sizes, small, medium and large. We also had to compare the performance of our new implementation with the original DSA setup from Phase 3. Finally, we were expected to conclude with analysis of which approach works better overall in terms of efficiency and security. To fulfill this requirement, we made the following changes. We used Blake2B as the hashing algorithm instead of SHA-256. For the key pair, we use RSA with a 2048-bit key instead of DSA. And for the signature scheme, we use PSS or probabilistic signature scheme instead of DSS.
Let's go through our code and explain the main component. First, we import the necessary modules. Time for measuring execution time, trace malloc for memory tracking, and for crypto, we use RSA, PSS, and Blake2B. The function test custom DSA is the core of our implementation. It does 3 things: generates RSA key pair, finds a given message using Blake2B hash plus PSS signature, verifies the message using the public key. Inside each of those steps, we use time.time to measure execution time and traceMalloc.getTraceMemory to track peak memory usage. We also test it on 3 messages of increasing size: short, high, medium, cybersecurity assignment 2025, long, important data, repeated 500 times. The results are stored in dictionaries and printed as neat tables.
Let's now run the code and look at the output tables. For time complexity in seconds, based on the results, we can observe the time taken by each operation for 3 different message sizes. For short one is 2 bytes, the medium is 29 bytes, and the long one is about 19,000 bytes. For key generation time, this operation took the longest, especially for short messages, which is 4.11 seconds for 2 bytes, 3.13 seconds for 29 bytes, and 3.21 seconds for 19,000 bytes. This variation is due to randomness in RSA key generation. Since it's only done once, the cost is acceptable. For signing time, the signing operation is consistently fast, around 0.019 to 0.027 seconds across all message sizes. Surprisingly, the signing time for the medium message is slightly higher, which is 0.027 seconds, likely due to background resource usage during testing. For verification time, the verification process is the fastest and very stable. All 3 messages took approximately around 0.003 seconds. This confirms our custom DSA is efficient even for large inputs. For the memory usage in kilobyte, let's look at the memory consumption. For key generation memory, around 15.08 kilobyte for the shortest message, 5.98 kilobyte for medium and long messages. This drop is likely due to system catching after the first execution. For the signing memory, 17.56 kilobyte for the short message, then reduced to around 8.9 kilobyte for medium and long ones. For verification memory, all 3 cases used exactly 5.63 kilobyte, proving that our implementation handles verification in a very stable and predictable way. Overall, our custom digital signature implementation using RSA, PSS, and Blake2B is fast and consistent, lightweight in memory usage, and doesn't degrade with longer messages.
Now, let's compare the performance of our custom DSA implementation in Phase 4. Firstly, in terms of speed, we can see that the key generation in Phase 4 takes 3 to 4 seconds, while in the Phase 3, it took about 13 seconds. Even though key generation is performed only once, this still shows a significant improvement. For message signing, our custom DSA also performs better. The range of the signing times is between 0.018 and 0.027 seconds in Phase 4, compared to 0.01 second in Phase 3. For verification, our Phase 4 approach is clearly faster. just taking around 0.003 seconds, while in phase 3, it takes around 0.017 to 0.018 seconds. Looking at the memory usage, our phase 4 implementation is much more lightweight. For example, the key generation in phase 3 consumed over 170 kilobytes, while in the phase 4, it's only used about 6 to 15 kilobytes. Memory usage for signing and verifying is also much lower and more consistent in phase 4. This shows that our algorithm scales well and is efficient even with the large message. On security side, we also notice improvement in phase 4. First, we replace DSS with PSS. Unlike DSS, which produce the same signature every time for the same message, while PSS adds random padding. This makes it harder for attackers to reverse engineer the private key or forge signatures, even if they know the original message. Next, instead of using SHA-256 like in phase 3, we switch to Blade 2B. It's faster and highly secure hash function. It also uses less memory and maintains strong cryptographic properties. Overall, this improvement makes our digital signature more secure, resistant to attacks, and suitable for real-world applications. To be concluded, our modified DSA system in phase 4 shows clear advantage in both speed and memory efficiency, especially during signing and verification process. Firstly, key generation was consistently faster in phase 3. Second, signing and verifying were not only faster, but also more consistent, regardless the machine's length. Lastly, memory usage was lower and more stable, making the implementation more scalable. For the side of the security, we upgrade from DSS and SHA-256 to PSS and Big2B.